All right, 4.2, day 1, okay? Looking specifically at function operations. All right, there's technically 5 different operations we can do with functions. Okay, we'll take a peek at 4 of them today. Operations we're pretty familiar with. That would be addition, subtraction, multiplication, and division. Okay, there's a 5th one called function composition that's a little bit different. We'll save that for day 2. Big ideas here, whether we think about it at a specific point or as a variable expression. We can do operations with functions. We can add them, subtract them, multiply, and divide them. Okay? A big thing to look at here that can confuse people is notation. Know that all of these things are equal, but this is the type of notation you see me use more often because I think it's more intuitive, it makes more sense. But know that if you see something like f plus g of x, that's saying the same thing of f of x plus g of x. So look at a few examples of just working with variables. Okay, here's the part A. This is exactly what I'm talking about. Okay, if I wanted to rewrite part A as f of x plus g of x, that's fine. That's saying the exact same thing. Okay. F is x plus 1. Now I should always have parentheses because technically those are there because I'm adding these whole quantities with each other. G is x squared minus 1. All right. Now there's really nothing to do with those parentheses because it's like distributing a 1, which isn't doing anything. So I can effectively just drop them. Plus 1 minus 1 cancel, and I get x squared plus x. Okay. I left x as a variable, and I added those two together, and I get a variable in my answer. Okay, again, that's f plus g. F minus g. Again, if you wanted to think about it this way, say f of x, that whole function, and then subtract the function g. Okay? Here's where parentheses get to be pretty important. We have x plus 1 minus x squared minus 1. Okay, the first parentheses I can drop, but here in the second one, I need to distribute that negative sign, and it becomes negative x squared plus 1. Okay, very important to keep track of that. So I have negative x squared plus x plus 2. Okay, negative x squared plus x plus 2. Okay, I get a totally different function when I subtract them. Okay, f times g. That would be x plus 1 times x squared minus 1. Okay, hopefully this just kind of reminds you of a little FOIL problem. Okay, first outside, inside, and last. Multiplying the first two, I get x to the third minus x. The inner two have a product of plus x squared and minus 1. All I have to do with this is just rearrange the order here. X to the third plus x squared minus x minus 1. Okay? One thing to check if you are doing a ratio of two functions. I'm doing f divided by g here. Oftentimes it's not possible to simplify. Okay? Usually when it is, it involves something like this, where I can take the bottom term, which is a quadratic, and I can factor it. That's typically what you need to look out for when you're dividing two functions, is factoring. Okay, that can be split up as x plus 1 and x minus 1. Those cancel, and the fully simplified answer there would be 1 over x minus 1. Okay, so these are all examples of working with operations of functions with variables. Okay, I can also work with functions as constants at specific points. Okay, for example, here I want to do f of 1 minus g of 1, which again, I think it's important to note that this is the same thing as saying f minus g of 1, okay? I'm talking about part A here. Saying the same thing, that's f minus g of 1, okay? Now, I don't have a variable in for x. I have a constant, okay? And I can see from the graph here, I'm going to zoom in a little closer. F of 1 appears to be 2, okay? F of 1 looks like it's 2. That's the y value at that point, all right? G of 1 is right there. It looks to be 1, okay? And this, again, this comes from the fact that f of 1 equals 2, g of 1 equals 1, 2 minus 1 is 1. And what this means on the graph is there is a difference right here of 1 unit, okay? Because again, this point on function f has the coordinate point 1, 2, and for g, it's the coordinates 1, 1. And what I'm really doing is just subtracting the y values, okay? Part B, when is the difference between the two positive? All right, let's go with where they're 0. Okay, that'd be a good thing to look at here. That's really where do these intersect? Okay, looks like right here at x equals 0, and here at x equals 4, those two graphs intersect and they're the same value. All right. What intervals is g of x, or f of x minus g of x positive? Okay, well that's essentially saying where is the blue graph above the red? Okay, that if this point right here that I looked at, that would include that point because the difference there was a positive number. Because when I did f of 1, I got 2, and when I did g of 1, I got 1. Okay? Now they are equal at 0. But it looks like between 0 and 4 is when the blue graph is higher and therefore has a positive difference. When is it negative? That's the exact opposite. Looks like when x is less than 0 and when x is greater than 4, that's when the red graph, which again represents g, which would be right here and right here, okay, it is greater than the blue. Where is it the maximum, f of x minus g of x? Where is that as big as possible? Okay? Looks like that's right here. Again, this would be the biggest gap between the blue and the red. Okay? And again, it's saying where is f of x minus g of x? So I want the biggest gap between the blue and the red. Okay? Now that looks like there's a difference of 2. Okay? And this all looks like it's happening at x equals 3. So it appears to me that f of 3 minus g of 3, okay, and it looks like f of 3 is 2, g of 3 is 0. The difference there is 2, and that's the biggest I could make f of x minus g of x. At x equals 3, there's a difference between those two functions of 2. And that's as big as it's going to get. Exact same thing going on here. You know, just basically a second example of what we just looked at. Okay, f of 1, I'm locating that specific point on the graph. Again, when I put in a real number for x, I'm no longer dealing with variables. This is going to be an actual number answer. Okay. Looks like on here that f of 1 appears to be 0. G of 1 appears to be 2. Therefore, the difference between those points would be negative 2. And the points I'm talking about are right here. Because again, that's what's going on the graph at x equals 1. Okay? As far as zeros go, looks like those two graphs intercept at x equals 0, x equals 2, and x equals 5. Okay. Again, this is written as f minus g, so the blue graph is still f, it appears to be positive, or that the blue graph has a positive difference, that it's higher up, like right here. The blue graph is higher than red at x less than 0. Oh, and it appears that when x is between 2 and 5, greater than 2, less than 5, it's also greater. For negative, between 0 and 2, okay, that's where the red graph appears to be higher, and then for any x value bigger than 5, okay, they're equal at 5, but then the red graph seems to pass the blue one at that point. Okay, maximum value of f minus g, again, this is where on this graph is that difference as big as possible. Okay, looks like it's right here. Whoops, right there. Okay, that would be at the x value of, at x equals 3. Again, to kind of write all this out formally, it looks like it's f, the biggest possible value for that would be f of 3 minus g of 3. F of 3 appears to be 2, g of 3 is 0, and once again it looks like the difference there would be 2, okay, which is as big as it could possibly be. There's no point on the graph where the blue graph is more than 2 units higher than the red. Okay, so again, the big thing here, we can add, subtract, multiply, and divide functions. Okay, we can work with them as variable expressions, or we can evaluate at specific points and use those operations with real numbers. Okay, we saw examples of both. That's all for day 1, and again, we'll look at function composition in day 2.